Hello everyone, and welcome back to Maastricht Science Programme. Today's episode is brought to you by Jansu and me, Victor. We'll be answering questions that we asked people in Maastricht itself, and these questions are mostly revolving about space. So hope you enjoy this video. So, our first question is to explain the Big Bang. Most people have already heard of the Big Bang, but only a few can explain it. First point, the Big Bang happened 13.8 billion years ago. That's 9 zeros, so quite a lot of time ago. To compare with the Earth only exists since 4.54 billion years ago. The Big Bang is the starting point of the whole universe. But contrary to beliefs, it's not an explosion, but it was more like an expansion. In the very first moment of our universe, all the energy and matter was accumulated in a volume less than a trillionth the size of a point of a pin. Around it, there was absolutely nothing, as the universe was all that existed. At that moment, the temperature inside was so extremely high that all basic forces of nature were similar. So, gravitation, electromagnetism, weak and strong nuclear interactions were basically the same. Afterwards, for reasons that are still unknown today, the tiny universe that it first was started expanding. The temperature was still extremely high, and black holes started forming. As soon as they appeared, they vanished. As the universe continued to expand, it became less dense, and so at the same time less hot. As the temperature was going down, gravity separated itself from other forces, as well as strong nuclear forces. This released a gigantic reserve of stored energy. It triggered a rapid expansion of the size of the universe. It was known as the epoch of inflation. It distributed energy and matter throughout the whole universe respectively. Now we're getting into proven laboratory physics. At this point, the universe was hot enough for photons to convert their energy in matter and antimatter particle pairs spontaneously. After a short time, the pair of particles destroyed each other, coming back to the photon state. At one point, a phenomena changed the fate of our universe, and the reason for it is still unknown. The symmetry between matter and antimatter was broken. It was producing slightly more matter over antimatter. The universe also continued to get cooler, and so all the four forces in nature, gravity, strong nuclear forces, electromagnetism, and weak nuclear forces, became permanent. Because of the distinct decrease in the energy of the medium matter, and antimatter pairs could no longer be created spontaneously from the photons. Remaining matter, antimatter particles, vanished, leaving behind a universe with one matter particle per every 1 billion photon particles and no antimatter. Protons and neutrons assembled from the annihilations to become the simplest atomic nuclei. Meanwhile, free-roving electrons scattered the photons, creating an opaque soup of matter and energy. At this point, the universe was cooled down below a few thousand degrees Kelvin. This caused loose electrons to move slower enough to get snatched from the soup by the roving nuclei to make completed ions. The three lightest elements, hydrogen, helium, and lithium, were the first ones to form as a result. Over the first billion years, the universe continued to expand and cool as matter gravitated into galaxies, each containing hundreds of thousands of stars that continuously undergo fusion. High-mass stars continued to explode, scattering elements to the universe. After billions of years of this enrichment, a star was born that we call the Sun. And that is how the Big Bang led to the creation of our solar system and the rest of our universe. So this was the explanation for the Big Bang, and now we're going to get some more information coming from Dr. Gideon Kukuk. The question we asked him was, what are 3 misconceptions about the Big Bang?
Oh, hi! The starting point of the universe as we know it now in our models of theoretical physics is indeed the Big Bang, and there's a lot of misconceptions about the Big Bang. One of the misconceptions is that it was this huge explosion that came with a lot of sound. Now, of course, in order to have sound, you need some material through which the sound can travel. Usually when I speak, for instance, that will be air, but it also works in water. But at least you need something through which the sound can travel. But around the Big Bang, of course, there wasn't any material yet because that was created in the Big Bang. So that means there was no sound to be made. You could have had your ear there, you wouldn't have heard anything. So it wasn't an explosion in that sense, like you would have exploded a stick of dynamite, for instance. A second misconception is that this explosion, this Big Bang, came with a huge flash of light, again like a stick of dynamite or a firecracker that you would lit. That also didn't happen. Sure, there was energy in the Big Bang and it came in all kinds of forms, for instance in photons, which are particles of light, but these particles of light were trapped within the matter. You have all this matter that was created and the photons were traveling between these particles of matter, but they would get trapped by these particles. And it was only after 400,000 years after the Big Bang, about 380,000 years, only then did those particles of light get freed from these particles of matter, and only then did the universe become transparent. You could actually see something. So the Big Bang wasn't a big explosion in sound or light. Now, a third misconception that people have about the Big Bang is that the universe started to expand at that point, which is by itself correct, but that the expansion then happened within a bigger space, right? If something expands, you need space around it in which the thing can expand. But this is not what is meant by the expansion of the universe. And one thing to demonstrate this with is, for instance, this ribbon here, which I think is going to be good if I show it up close. If this were the universe, it's a one-dimensional universe, it only extends in one direction, then you see all kinds of points on this universe, these little dots. And one way to make this universe bigger is just to make sure that I have extra ribbon coming on both sides. And then you can ask the question, well, what is around this ribbon in which these extra parts could be added? But this is not what is meant by the expansion of the universe. By the expansion of the universe is meant that if you would look at the dots on this ribbon and the universe expands, then every two dots will expand away from each other. And this kind of expansion does not require a boundary. It doesn't require a bigger space to be in. The only thing that it requires is an existing amount of space and it stretching away so any 2 points can get away from each other. That even works without having a boundary and therefore without necessitating the question what is around the universe. That, I think, were the three biggest misconceptions about the Big Bang.
The beginning of our solar system started as a big cloud of dust, but there was no sun. It started 4.6 billion years ago. It was called a solar nebula. Gravity took matter into its own hands and formed the sun at the center. Luckily, there was enough heavy elements present in the gas cloud around the sun for them to aggregate and form planets. Surrounding those planets, there were billions of asteroids, which collided between each other and also collided with planets. Also comets were present. Because asteroids kept hitting the former Earth's mantle, their surface was completely molten, so life was impossible. Another smaller planet crashed on the Earth. The two fused, and the debris surrounding the Earth congregated into forming our new moon. So now our second question is, can we live on the moon? And also, are we going to colonize it and also colonize other planets? We'll also have an interview from Dr. Gideon Koekkoek.
I see no reason why humankind cannot colonize any other planets or our moon or Mars or maybe one of the planets even much further away, because there's no principal difficulty from physics. There's nothing in physics that says that you cannot build a rocket, just hop on board, fly there, land the rocket and build whatever you need to colonize, like houses and greenhouses and these sorts of things. There's no reason in physics that you cannot do that. The reason that it is difficult is just pragmatism. First of all, it takes an enormous amount of energy to make a rocket get loose from the Earth and actually fly someplace. And the more stuff you try to squeeze in there, for instance, all the materials that you need to build your colony, the more difficult it is, the more energy it costs. So the reason is much more pragmatism than physical impossibility. So I suspect that people will colonize at some point, but it might take a while. Now, if you're going to colonize, then it's going to be a lot easier to colonize something that is close to the Earth, and that will be the moon in this case, because it's only 400,000 kilometers apart. That means that if you're there and you find that you're missing something or something goes wrong, it's not that difficult to get back. But if you go, for instance, to Mars, which is much further away, the planet Mars, then if you go there, you better be sure that everything is done and planned correctly, because if something goes wrong, you're in really deep trouble. Now, finally, there's in principle the option of going to planets outside the solar system and go there and colonize those planets there. It just happens that these planets are ridiculously far away because you have to go to another star, and the star that is closest by Earth is already at 4 light years. And that means that light itself, which goes with a ridiculously high velocity of 300,000 kilometers per second, takes 4 years to get there. Now we, our rockets, cannot nearly go with that velocity, so it takes us hundreds, thousands, 10,000 of years to get there. And I think you're going to have difficulty finding volunteers who want to sit on a rocket for 10,000 years before they finally reach their destination. So I think it's going to take a while before we're going to colonize, if ever, planets away from the solar system, closest by Mars or the Moon.
As of our last question, is anybody out there? So, is alien life possible? And for this last one, we'll also have an interview from Dr. Gideon Koekkoek.
Well, I do think that alien life is possible, and it's not because we've actually seen alien life, despite there being all kinds of efforts to look into the universe and hopefully see alien life. It hasn't been seen yet. Now the reason for that is twofold. One of them is that it takes an enormous amount of time before you travel from one place to the next. So even if there's a planet out there with alien life on it, then it's going to take millions and millions of years, depending how far away it is, before that life could have traveled here. Even when they send out their signals, that they don't themselves go here, but they send a light signal towards us, for instance. That too takes multiple years to get here. So even if there is life and they're trying to communicate with us or actually actively travel here, then it's going to take an enormous amount of time before they get here. That's one reason. And the second reason is you have to know where to go, right? If we have to go to some other place somewhere in the universe because we think there might be life, there's an enormously big chance that you're not going to go to the right place. And the universe is really big, so the chance of you going into the right direction are actually not that big. Now, but we do think that there is life. Again, not because we've seen it, for the reasons I just told you before, but the reason that we do think that there is life is simply out of statistics. For the life that we know that can exist, which is our type of form of life, so it's made out of carbon, and it needs this amount of light, and it needs this amount of energy, and it needs this amount of shielding from radiation coming from the universe, all these things, we know that it can happen because at the very least it has already happened here. Now, for this type of life, you only need the right circumstances. Now, how big are the chances of finding these circumstances? Well, actually not that big. You have to have exactly the right planet with this mass and with this shielding from radiation, with this temperature, all these things. But even with a very small probability of finding life or the right circumstance of life at a certain planet, the universe is ridiculously big. We know that many of the stars that we see have planets around them. We also know that there's hundreds and hundreds of millions of stars. Now, even with an extremely small chance of one of these planets having life, you have so many planets that it would be statistically almost impossible not to find a planet that has the same circumstances that we have on Earth. So just for that statistical reason alone, we highly expect there to be life out there. And it's actually a little bit better than that, because this argument is based on the assumption that that life needs our particular set of circumstances. But there might very well be that evolution has decided that other circumstances work just as well, and that means that the chances of life are even bigger. We don't have to look for circumstances that look like ours. Other circumstances will do as well, which increases the chances. Now, why haven't we seen that life? Well, for the reason that I said before, it's very far away at the very most likely. And that life will have to know where to look in order to find us, or we have to know where to look in order to find them. And there's where the difficulty lies.
So this is the end of this episode. A big thank you to all the people to who we asked questions, and also a big thank you to Dr. Gideon that accepted our invitation for an interview. So check out our other videos and drop a like. Thank you.